Hey, it's me. It's your pocket hero. And in today's lesson, we'll talk a little bit about physics, what is it, what does it do, and then we'll talk about units of measurement, the fundamental ones and then derived ones. First of all, what is physics? Well, the term physics comes from the ancient Greek physike and means the knowledge of nature. So, physics itself is the study of nature itself. And why are we studying physics? Well, let's try to think of this simple theoretical experiment. Let's imagine to jump onto a time machine. And let's go back to 100, 200 years ago. We didn't have electricity, we just had candles. We didn't have mobile phones, we didn't have internet, cars, trains, airplanes, whatsoever. It was just a boring and very tough times, right? And all the developments that we achieved during these only 2 centuries was thanks to physicists and mathematicians that allowed us to explore and better understand nature and how to build those kind of devices. What does physics do? Well, physics studies natural phenomena. It studies how light behaves, how matter behaves, and all those kind of interactions that we experience every day. Physics talks about quantities, and it quantifies things that can be measured, like mass, speed, current, and so on. This means that physics doesn't deal with things like love, like emotions. And what's the goal of physics? Well, physicists and physics itself try to find some laws that can be used to describe and even more importantly to predict reality. Which are the fields in physics? Well, we have different fields. First of all, we have the simplest one and even the oldest one, that is mechanics. Then we have thermodynamics. We have optics. We have acoustics, electromagnetism, atomic physics or quantum physics. And then we have relativistic physics. These are all different fields in physics, and I think that all of them are incredibly interesting. But what does physics deal with? So we need quantities. Physics measures quantities. We said that we deal with something that is quantifiable, so we need quantities. But what's measuring and how can we measure? Well, first of all, we need a unit of measurement. And then once we have a unit of measurement, measuring a quantity means saying how many times the chosen unit of measurement fits in that quantity. For example, saying that a table is 2 meters long, it means that in the length of the table we can fit 2 times the unit of measurement of length, that is the meter. So in that 2 meter table we can fit 1 meter 2 times. But which are the units of measurement? Well, we have 7 fundamental units of measurement. All the others are derived, but we have 7 units in the International Standard System. The International Standard System is based on the metric system. Sorry, American. And these units of measurement are the following. So the first one, second, that is used to measure time, meter for length, kilogram for mass. Be careful that it's not weight, because for weight we use newtons. Ampere, that is used to measure current. Kelvin for thermodynamic temperature, or just temperature. Mole, that is used to measure the amount of substance. And candela for luminous intensity. A second is defined as the duration of 9,192,631,770 periods of the radiation corresponding to the transition between the 2 hyperfine levels of the ground state of cesium-133 atom. This is just the definition of second. It's kind of hard to understand. It's something that some dudes agreed upon to define it in scientific terms, we don't really care about it, about vibration of ground state, hyperfine level, cesium-133. What does it mean? Well, what you need to understand is what is the concept of time. Well, time is the occurring of events, one after the other. And you can actually perceive the passing of time. Just remember when you were a kid. Then you're a teen, then eventually will become an adult and an old person, right? You can never go back. So you have a series of events that continuously occur, they never go backwards. So time follows an arrow, the arrow of time that can only go forwards. And we quantify time by counting how many seconds fit in that amount of time. So we have the definition of second, we know how much it lasts, we have our phones, we know how many seconds we have in a minute, in an hour, in a year, in 10 years, right? So we just count how many seconds fit in that amount of time. And this is the measurement of time. A meter is defined as the distance traveled by light in vacuum in 1/299,792,458 of a second. This is the definition of a meter. But what does it mean? Well, the definition, the scientific definition, is based on something called a universal constant, that is the speed of light. What does it mean to be a universal constant? Well, it means that this quantity, the speed of light, is always constant everywhere in the universe. So it's very useful to define something considering this kind of constant, right? Because they don't change. So the definition of meter cannot change anywhere in the universe. So once we have a meter, that is this fundamental unit, we can measure lengths, areas, and space. So with the meter we can measure lengths. Lengths, they live just in one dimension. Just try to imagine a single line. This line lives in only one dimension, and we measure how many times a meter fits in that length. An area instead lives in two dimensions, so we cannot really use just a meter. We will use something called a derived unit of measurement, that is the area. Area is defined as square meters. And when we measure areas, we measure how many times a squared meter fits in that area. While to measure volumes, we use a different units of measurement that is still a derived one, that is the cubic meter. So in order to measure a volume, we measure how many times that cubic meter fits in that volume. Length and space itself can behave differently from time. We've seen that time only follows a single arrow, the forward one. We can never go backwards in time. But for space and length, well, we can actually go backwards. But what's important is that we can never go to negative spaces. They do not exist in real life. And how can we imagine the difference between 2D space and 3D space? Well, try to think at your screen, where you're watching YouTube. It lives in two dimensions. It doesn't have a depth. You cannot go inside the screen. Even though it's depicting something that maybe is happening in 3D, like Minecraft, like a video of real life, you cannot enter it. So you can only see it in two dimensions. While you live in three dimensions, you can go backward, forward, up and down, right and left, right? And this is the difference of three dimensions. The definition of kilogram has been changed this year, in 2019, and it starts from the definition of the exact Planck constant, that is h. h has been set to be equal to 6.6260715 times 10 to the minus 34 joule times second. Well, joule is derived unit of measurement, and it's equal to kilograms times meter to the second times second to the minus 2. So once the definition of meter and second has been set, then 1 kilogram equals h over 6.6260715 times 10 to the minus 34 meter to the second seconds to the minus 1. So the definition of a kilogram is based on some agreements, right? But what does it actually mean? Well, we have the unit of measurement, it's been defined by someone else, and what do we measure with the kilogram? Well, with the kilogram we measure mass, and mass is the amount of matter. So the amount of matter is the total amount of atoms that constitute a given body. And mass can also be seen as the resistance that this body has to acceleration. A simple example is, let's imagine that you're running very, very fast, and then you want to stop suddenly. Well, it's kind of impossible, right? You need to slow down, and then you can actually stop. This is because you own a mass, and a mass is difficult to stop because you need to put in some work, some energy to stop it. And the more mass you have, the harder it is to stop you. The next four fundamental units of measurement cannot be understood that intuitively, like for mass, time, and space. What we will do is that we will take care of them, we'll explain them in depth when we will talk about topics that will need them in future videos. The definition of ampere is the flow of 1 over 1.602176 times 10 to the minus 19 times the elementary charge E per second. The definition of Kelvin changed in 2019 as well, and it's based on the setting of the Boltzmann constant K as equal to 1.380649 times 10 to the minus 23 Joule times Kelvin to the minus 1, and is obtained given the definition of kilogram, meter, and second. The definition of mole is the amount of substance of exactly an Avogadro number of elementary entities. The Avogadro number is equal to 6.0221476 times 10 to the 23. While the candela is defined as the luminous intensity in a given direction of a source that emits monochromatic radiation of frequency 5.4 times 10 to the 14 Hz. Now, definitions of the units of measurement is not that important, but you need to understand that we only have 7 fundamental ones. All the other units of measurement, like square meter is the units of measurement of area, the cubic meter, or whatsoever, they are just derived units of measurement. Another example of a derived unit of measurement is the density. Well, density is defined as the ratio of mass over volume, and its unit of measurement is kilogram over cubic meter. This means that the density is directly proportional to the mass of a given object, while it's inversely proportional to the volume of the same object. Some other examples of derived units of measurement that have special names and symbols are these ones. So we can see that some of the most important ones are the units of measurement for force, that is Newton, for pressure, that is the Pascal, for energy, very important, that is the Joule, power, that is the Watt, electrical charge, that is the Coulomb, and so on. So we can see that probably we'll use most of them during our lessons, and they are very important. But you can notice that you can always go back to the International System base unit, and we can always express them with those fundamental units. That's why they are called derived. Some other ones that are very important can be the kinematic ones that are, for example, speed or velocity, which its unit of measurement is meters over second. Acceleration, that is meter over second to the second power. Angular velocity, that is radian per second. And angular acceleration, that is radian per second to the second power. So we can see that we have many and different units of measurement. They are kind of a lot and complex, but you'll get used to them. I mean, using them many times, you get to learn them, you get to be more experienced with them and even more confident. So I hope you enjoyed this first lesson. Please leave a comment, let me know if you would like to learn something more, if this was useful for you. I think that this part is kind of easy, so I'm not planning on doing any exercises on these topics, but please let me know would you need them. And remember, physics is beautiful. Bye bye.